Welcome back to the course in nuclear medicine physics. Today, we'll be looking at nuclear counting statistics. In particular, we'll discuss both systematic and statistical errors. We'll then look at particular distributions that are relevant to counting, like the Poisson distribution and the Gaussian distribution. Finally, we'll take a quick look at error propagation and applications in nuclear medicine as well. Let's get to it.
So quickly, there are different types of measurement error. We're going to talk about Poisson distribution, which is very important, Gaussian distribution, background radiation issues, propagation of error. Actually, I won't really talk about statistical tests today. So anyhow, so there's three types of measurement error. One are just blunders, like gross inaccurate mistakes, like somebody makes the wrong selection on an instrumental setting. Like you're doing a PET scan involving F18, but you tell the scanner this is actually C11. So if, for example, it would do the incorrect positron or branching ratio correction, et cetera, et cetera. So these are just mistakes, and mistakes will always happen. Operators will always, like humans, will always make mistakes, and that's just a fact of life. So we're going to get some outliers. And often, how do you say something is an outlier? And, I've seen many, many examples where people are doing some experiment and something doesn't fit anything. They just say, oh, it's an outlier, we're going to throw it out. But that's not correct. There are actual tests, such as the Thompson criteria, that really tells you this is, for all practical purposes and with a very high probability, an outlier. Maybe only when you do that test, you can sort of really call it an outlier. But often what happens with an outlier is, hopefully you don't just throw it away. You will go back and try to correct it. I remember years ago, this is like maybe 20 years ago, we had an invited speaker here at the physics department at UBC. And just before he was here to arrive to give a talk, he won the Nobel Prize. And I think he was from Stanford. And in fact, once I actually saw him in Stanford just by total accident. And he ended up honoring the invitation. He showed up and he gave this lecture, and the room was packed with people. This is so exciting. This guy just won the Nobel Prize in physics. We were all sitting watching him. And I remember he showed this diagram, and he said, this is why I won the Nobel Prize. And the diagram had he was supposed to give you a nice linear fit, but he noticed that after a certain point, he couldn't fit the data with the line, and he had to change the slope a little bit. And he could have called it an outlier and totally ignored that point. But he ended up actually paying attention to this phenomena. He ended up discovering this whole phenomena. I think it was helium related or whatever it was, and he won the Nobel Prize. So, I'm saying that you can't just get rid of outliers. Outliers often allow us to have major discoveries, or sometimes they allow us to have major discoveries. You have to understand. So often when we have outliers, we go back to the data and we realize, oh, somebody did this wrong. So we redo the calculation, and then we get the data to work better. So how to really avoid it, you just have to be careful, but it will happen, and you just have to go back and be systematic about it. But a far more common measurement error are systematic errors. And so these are things that are consistently different or off or wrong. So repeated use of a malfunctioning measuring device. If you have not done proper quality check, and we will have lectures in the future talking about quality check or quality assurance. If you don't do proper quality check, you may have a PET scanner or a SPECT camera or a gamma camera that is malfunctioning and you're not realizing it. So it's consistently giving you wrong answers. And if you're comparing two groups that are not matched for age, for example. So results may be precise, but are not accurate. Okay, so this is the difference between precision and accuracy. I remember, just to give you another story, when I was defending my PhD thesis, I was kind of stressed out and people were asking me questions. Somebody asked me, what is the difference between precision and accuracy? And I've said this to many people. I was stressed and I was like, oh, I just sort of guessed it because I was, under pressure, and I got it right. But this has always stuck with me. We should know the difference between precision and accuracy. So here we're dealing with something that may give you the exact same answer over and over and over again, but this is the wrong answer. So you could tell someone you are precisely wrong, right? So it's a systematic error. So multiple measurements of a sample may be all very similar to one another, so that's precision, but biased. Okay, so bias measures that, whereas noise measures the precision aspects. Bias versus noise. This is why it's critical to have quality assurance. So I talked about that. Okay, so random errors, and I remember how I said in our field, radioactivity is inherently random. So we have an inherent randomness to radioactivity. On top of that, device measurements also have their own randomness. If you read something on a ruler, depending on the time of the day you're reading, or when you keep repeating it, you may read a number to be, a distance to be, 23.1 millimeters. The next day you may read the exact same thing, 23.2 millimeters. These are random errors that you may actually have from day to day. So a result of two things: either physical limitations of the measurement system, so reading a ruler by human eye, so there's noise in our detection, and variation in the measured quantity itself. So this is always the case in radiation counting measurements. Okay. Much of what follows focuses on how to characterize and analyze random error in statistical terms, so statistical error. So Poisson distribution is a very, very important distribution. If you have a large radioactive sample counted repeatedly, you're going to have Poisson distribution. In fact, you can derive the Poisson distribution assuming you have many, many, many nuclei, and only a very, very small fraction of them decay. And that gives you the Poisson distribution. And we won't derive it here. I think some of you might have seen it in undergraduate studies, how this is the Poisson distribution formula itself is derived by that assumption. But the point is, we have Poisson. The nature of radioactivity gives us Poisson noise. So if you have a sample of radioactivity here and a detector here, in one moment it may measure 10 counts. In another, let's say you're measuring over 1 minute. First 1 minute, 10 counts. Another 1 minute, another day, 9 counts, 8 counts, 12 counts, 13 counts. That noise, that distribution of counts is given by the Poisson distribution, which is given by this formula. And so you can sort of see if the true mean is around 1, the Poisson sort of spreads around. It's totally asymmetric because you cannot have negative counts, obviously. So you're going to have a high chance of getting 0 counts, 1 count, and then less and less chance of getting 2, 3, 4, etc. But if you have a lambda of 4, on average, if it's 4, you're going to have a distribution like this. And as lambda becomes larger and larger, the Poisson distribution starts to look like a Gaussian distribution. So variance is, of course, given by this formula. You all know this, the equations for standard deviation and for variance, or standard deviation is just the square root of variance. So this is the equation for variance when you have an infinite number of samples. Of course, in reality, we do not have an infinite number of measurements. So often people, instead of saying 1 over n, they say 1 over n minus 1. There is actually some good reasons why this is n minus 1. Some people actually disagree with this, but I won't go through that. But let's just use this equation for standard deviation. So in this case, we've got sample standard deviation. So sample standard deviation is an estimate of the true standard deviation. Anyhow, so you do that, and in a Gaussian distribution, about 2/3 of your measurements fall within 1 standard deviation, and 95% fall within 2 standard deviations. In the Cherry text, you may get the impression by reading it that this is true for all distributions, but it definitely is not true for all distributions. This is true. This 2/3 is true for Gaussian, and for Poisson, therefore, it's also true if you have larger number of mean values. But the thing you really have to remember for Poisson distribution, which is different than Gaussian, is that in Poisson distribution, the variance and the mean are intrinsically tied to each other. It's not, you don't have freedom. You cannot have a mean and a freedom of choosing your standard deviation, unlike a Gaussian. The variance is equal to the mean, or the standard deviation is equal to the square root of the mean. So if that's the case, and assuming sufficiently large mean numbers so that we can use this 2/3 or 68% of the data, essentially this means that about 2/3 of your data falls within the number of counts plus or minus the square root of that. Now, if you have a single measurement, well, you don't know what the true mean is. So you sort of assume that the mean is equal to that single measurement. So we write this rule like that. Let's see, are we having questions here? Okay, so we will get back to that. Yeah, let me go through those three measurements. Feel free to ask questions. I mean, there's no problem in asking any questions you like. So we will answer some, we won't answer some. It's totally fine. So please let everybody ask questions as they wish. Do not stop yourself from asking questions. Totally fine to ask any question that comes to your mind. So the percent uncertainty is given by this formula, and therefore we've got square root of n divided by n, so it's this formula. So you've got 100 counts measured by a sample. Well, in a Poisson distribution, the standard deviation is the square root of that, so it's 10 divided by 100, so it's 10%. You've got 10,000, then it's 100. Square root of that is 100. 100 divided by 10,000 is 1%. So obviously, as you can see, if you count for longer, so you collect more counts, you're more certain there's less variance. So just remember this formula, the square root of n is the standard deviation. Whereas in a Gaussian distribution, that is not true. In a Gaussian distribution, again, the mean can be different than this, totally decoupled from the standard deviation. But in a Poisson distribution, that's not the case. These two are inherently linked to each other. So in a sense, you only have 1 degree of freedom, unlike a Gaussian, which has 2 degrees of freedom. So here's an examples on what happens when you have additional random errors. Like, for example, you have an error in the measurement instrument that you add to it. You can refer to this Cherry textbook if you have it. If you don't have it, don't really worry about it at all. We're not going to ask you questions if we're not providing you the material, unless the question is directly using this equation that you're being provided. Now, so how do you propagate errors? How do you propagate errors? Yeah, so we're asking a question. Thank you, Ivan. Fantastic question. Why is lambda equal to the mean? Yeah. So I think there's this lambda is not necessarily the same lambda as we had before. So I want to be very clear. Let me go back to the notes. Yeah, I think that might create some confusion here. The lambda that we use in the Poisson formula, this is not the same as the lambda we were talking about as the law of decay before. So that's just a similar lambda. It looks like the similar lambda, but it's not the same lambda. So here's by lambda, we simply mean the mean count. It's the actual average number of radioactive decays. Whereas previously, lambda was the decay rate compared to the total number of counts. So it's not the same. Good question. So thank you. So I hope that answers well. Yeah, this lambda is different than that lambda. We had, the exponential law, e to the power of minus lambda t. This lambda is not that. This lambda is, let's say you have you're measuring something in 1 minute. What is the true number of average counts you're going to measure in 1 minute in this sample? That's lambda. Thank you. Great question. And thanks for that, helping me clarify that, Yvonne. So how do you propagate errors? You've got different means, different lambdas. You want to do subtraction, addition, etc. How do we do it? Well, this is a general formula. Has nothing to do with radioactivity. This is just a general formula you guys should know. When you're adding uncertainties or subtracting uncertainties, the error in them always adds. Even if you're subtracting, the error adds in squares. This is a general formula. Now, of course, you could do the math and say sigma squared is equal to n in the case of Poisson distribution. So you can substitute and get this. Frankly, I don't memorize these formulas. In the Cherry text, they have all these different formulas. I really don't memorize these at all. I only know this, and many of you already know this from undergraduate studies, that when you add or subtract uncertainties, the associated lambda just adds in quadrature. And you just have to know this additional rule and you're set to go. So for example, What's 100 minus 96? That's a great, what is it, 3 question or whatever. Of course, we're not testing anybody on doing this, but what is 100 minus 96 in terms of noise propagation? So you've got 100 is plus or minus square root of 100. So if you measure, if for example, you measure 100 counts and in some study, and I measure 96 counts in another study, somebody asks you what is the difference between these two? Well, obviously it's 4, but 4 plus or minus what? So it's 100 plus or minus square root of 100 minus 96 plus or minus square root of 96. And these, as we said before, they add in quadrature. So you square this plus square of that, you take the square of that, you get 14. So actually subtraction can give you very large errors. So we've got 4 plus or minus 14. That's like a 350% error. So we're very, very uncertain. If you measure 100 counts and I measure 96 counts in a counter, the difference is 4, but we're very uncertain about how true that is. Now for multiplication and division, again, you've seen this in undergraduate studies. If you're multiplying or dividing, again, you add only, but you add the percent uncertainties, not the absolute uncertainties. So first you have to convert your standard deviation to a percentage, then you add them in quadratures. So again, let's ask you a question. What's 200 divided by 100? You measure 200 counts, I measure 100 counts. Somebody asks you what is the ratio between these two measurements? Well, of course it's 2, but 2 plus or minus what? How certain am I that this ratio is 2? Again, you go through the math. This is 200 plus or minus square root of 200, but you have to convert this now to a percentage. So it's 7% for this and 10% for that. Then you add this 7% and 10% in quadrature like this, and you get this number. So the ratio of these two numbers is 2 plus or minus 12%. Again, you could sort of put these equations in there, blah, 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 but I really don't memorize these at all, even though some textbooks write them. I just memorize the general rule. And then I just know that you just have to put this square root for the standard deviation. That's it. Now, if you're doing a constant multiplier, well, it's very simple, and you can easily prove this. The percent error remains the same. You can show it because the standard deviation simply multiplies. So if k is a constant multiplier, like a fixed number, like if there's zero uncertainty associated with k, like let's say you just say, you gave me 200 counts, what's that multiplied by 2? An exact 2, not an uncertain 2, an exact. I just want you to multiply that by 2. If you were counting, twice as much, what would you get? Well, it's twice as much in absolute standard deviation, but in percentage, it's the same percent error. So therefore, the percent uncertainty remains exactly the same by multiplication or division by a constant number. And finally, if you're averaging, this is why averaging is such a good thing. It's good for all of us, multiple of us, to be making measurements and then averaging the results, because it turns out in general that the standard deviation of the mean is equal to the standard deviation of, in one measurement, divided by square root of the number of measurements that we're making, number of samples that we are collecting. Let's say 10 of us are going to the field and making, measurements of something. And this is true in general. Now, there are some formulas. Again, I don't memorize these formulas, but you may want to memorize, if you really were to memorize something, you may want to memorize this formula. But I don't have it memorized in my own mind. So for count rates, you can actually show a count rate is the number of samples you measure divided by time. Remember, time is a constant multiplier. Let's assume time you measure very, very, very accurately. Let's assume there's not much error associated with time. Then you have this formula, you put it in here, and you can bring the t inside, you get this, n over t is r, so you sort of get this equation. So the standard deviation of the rate, not the number of counts you measure, the rate of that you measure is given by this formula. Okay? And you can also calculate it for percent uncertainty. Again, frankly, I don't memorize this formula. Now, effect of background radiation is important. There's this thing that we refer to. So, all nuclear counting instruments have some background counting rates. And so this could be from electronic noise, detection of cosmic rays, natural radioactivity in the detectors themselves. Some detectors are inherently radioactive a little bit. We will see this in PET imaging. I think hopefully we will discuss that. So there's this background radioactivity. So that interferes with actual measurements. So this thing we call minimum detectable activity is defined as that activity which increases the counts recorded by an amount that is statistically significant compared to background counts. So typically, people say that if the rate is more than 3 times the standard deviation of the background, we call that minimum detectable activity. So for a rate, so we're talking about rate, not number, but rate. That's number divided by time. If the rate is equal to 3 standard deviations of the background, that's a minimum detectable activity. So then you could sort of say, 3, based on the previous page equation, you sort of arrive at this. Okay. That's it. That's it for here.